Welcome to this video on energy emission and absorption, and this is part 2. In part 2, we're going to be taking a look at a little bit more detail and building our understanding of how in the Bohr model of the atom we can understand why only certain colors are being emitted when we excite a gas of a particular element. If you haven't checked out part 1, go ahead and check that out because it lays a good foundation for what we need to understand here. Additionally, I'm using some images, again, the ones I haven't created, from the openstacks.org texts, and I have a link in the description below to their awesome resources. So over here I have two different emission spectra. The top one is for a hydrogen atom, and we saw that one in the last video. And the bottom one here is for a much heavier atom with a higher atomic number, and that is iron in this particular case. And you can see that they're vastly different. The larger the atom becomes, the higher the atomic number, the greater the amount of spectral lines that we end up seeing. So it becomes more and more complex as the atoms become more and more complex. And so for that reason, we're going to be focusing mainly on the hydrogen atom in these videos in order to help us understand the basics, and we can build on that later. Now, if we recall, these emission spectra were implying that when light interacts with a particular element, the element absorbs a lot of energy and emits only certain discrete amounts of energy that we refer to as being quantized. So in here, we're going to start to look at what Bohr proposed, Niels Bohr proposed in 1913 as the particular structure that could support the experimental evidence. And that was kind of almost a planetary model. So we have this nucleus over here, which would be analogous to the sun, and then we have these electrons that kind of rotate around this nucleus. Now that's a little bit of an archaic view, but it gives us a very good understanding to help us get started. So if we remember from our electrostatics studies, we know that a positive and a negative charge are naturally attracted to one another. So I could calculate the energy between this electron and the nucleus here by saying that if I know the kinetic energy of the electron and I add that to the potential energy of the electron, what I end up getting is a value that would describe the energy that this electron has in total, its total mechanical energy. And because when it's tightly bound here, the U value, the potential energy, is going to be a negative value. So we're going to end up with a negative amount of energy that I'm going to call E sub 0. Now this is the optimal energy that a hydrogen atom will want to use, and it's not really a desire at all, it's just naturally what the element will have when the electron's moving at a very particular speed, and that amount of energy in electron volts is negative 13.6 electron volts, and we'll see where that number comes from in a minute. But the basic idea is that I could literally put 1/2 mv squared plus m over r times g, the gravitational constant, and I could actually calculate this value as being the amount of energy associated with that position. So this is what we refer to as the ground state of the hydrogen atom. Ground state meaning it's at its most basic energy state. It's the most efficient and the most naturally found state in nature. So it has the optimal, almost like a Goldilocks amount of energy to hold it at that particular position. Now, what we saw happening in the last video was we excited the gas. So the gas is made up of a lot of these. And when we excited the gas, what we saw was that it emitted energy, and the energy that it emitted came out only in these discrete wavelength amounts. Now, when we want to calculate the amount of energy that's associated with a particular wavelength or frequency, we know that we can use Planck's equation, the Planck's constant times frequency, or h times the speed of light over wavelength. And these are equivalent just depending on if you're using wavelength or frequency. So we see that if we want to get the electron to move outwards here, okay, we studied in electrostatics that positive and negative charges are naturally attracted. So in order to separate the charge, it's going to require an external supply of work or energy. So what's going to have to happen here is, in order to move from the ground state, which is the naturally occurring state, in order to go from that to what we refer to as an excited state, we're going to have to put energy in to the system. So energy going in the form of a photon. And the energy in the form of the photon, again, can be calculated with HF or HC over lambda. That is going to allow the electron to stay there, but unless I continuously supply this energy, what's going to happen is the electron is going to want to fall back down to its lower energy level. And when we go this opposite direction, so I'll do this here in a different color, if we go from an excited state back down to the ground state, what's going to happen is energy is going to be released or emitted, and that's going to be, again, in the form of a photon, and the photon's energy can be calculated, again, with HF or HC over lambda. So the basic premise here is that moving to a higher or excited state will absorb energy, and when the electron falls back down to its lower energy state or its ground state, it will then emit energy. So what we're seeing here is the energy that's emitted by the hydrogen atom when the electrons fall back down to their ground state. Now what this implies, because there's lots of different wavelengths here, you can see we have this purple here, like a dark blue, here maybe an aqua color, and then a red, is that it must be falling down from many different excited states. So there's not only one excited state. And we refer to these different states as N levels, sometimes also written as M levels. So these N levels just describe the quantum state that the particular atom is in. So we could have something like N equals 2 or N equals 3 or so on. And these N values are always going to be whole number integers. And if you're thinking of the example that we talked about before with the steps, you might think about labeling each step as N equals 2, 3, or so on. The ground state is going to be N equals 1, which will be the most basic and most favorable energy state, the lowest energy required to stay at that point. Now, if I gave the atom enough energy, a special case, which we're going to refer to as the energy at N level infinity, that's just implying that it's no longer bound to the atom. So when you're no longer bound to the atom, you have no energy associated with that particular position. Whereas each of these other levels are going to require more and more energy in order to get to as we move up the scale. So a way that they show that is through what we call this energy line diagram over here. And the line diagram is just a visual tool to help us see how the energy differs from each level. So here we have the N equals 1 level, and we might write that the amount of energy associated with that is negative 13.6 electron volts. This is particularly for hydrogen. Then if we move up to the N equals 2 level, this is going to be a different amount of energy. And then if we move to the N equals 3 level, a different amount of energy. But the energy levels get closer and closer to one another in quantity and in gap distance in the drawing. That shows us that as you get further and further out, eventually you will reach N equals infinity, and there at that level you would say that there's no energy needed to be at that level because you're not even associated with the atom anymore. Now what we're going to look at in part 3 is how to actually calculate the energy difference and how to actually calculate the wavelength of these very unique and discrete values of the different emission spectra.